Hey folks, in this video we're going to be looking at building an Elm app from scratch using the Hangman guessing game as an example. I'm going to use it to go through the basic structure of an Elm app and relate it a little bit to React and Redux. Also look at how to do interactivity, an HTTP request, a tiny bit of JSON decoding, and how to use custom types in order to specify and manage our state more easily. I really love Elm. It's a clean and simple language. The compiler is super fast and has helpful error messages, which leads to a really nice development flow. And the final code is often robust and really easy to refactor, which is super important on large projects. Let's go and have a look.
Okay, so we're here inside an empty folder. To get started, I'm going to use create Elm app, which means I need to install it. I tend to use yarn. I tend not to install anything globally, so I'm going to install it into this directory now. Okay, I'm going to clear this. I'm also going to install Elm format, which is the main code formatter used in the Elm ecosystem. Okay, I'm going to clear that too. Now my current directory has the package.json, the yarn lock, and the node modules. I want the node modules.bin folder on my path so that I can access the Elm compiler and Elm format and the create Elm app. So I'm going to run this command, which is going to do that. Now I can run Elm if I want, or Elm format, or create Elm app. And if I run this with Hangman as the directory name for the project we're creating, then it's going to set up that project for me. Great, so now I can go into Hangman and as recommended, I can run Elm app starts to get the server going. But first I'm going to run tmux so that I can get two different tabs. So I can run the server in one and be editing in the other one. This is just a preference of my setup. You're welcome to use any approach you like. Okay, so I can run Elm app start in this tab to get the server started. And this has launched my browser with the correct URL for the local server and is showing me the kind of initial setup they have within the automatically generated Elm project. So it's just showing you that the basic setup is working. If I come back to my tabs and go into the other one and open the main Elm file with my editor, then we can see the structure of a basic Elm app setup. So we mentioned that Elm was quite like React and Redux. So in Redux you have state, you have some way of changing the state, I think it's called a reducer, and then you have kind of the React components which form your view. In Elm we have the model, which is your state, init, which is a way of creating the initial version of your state, the update function, which serves the role to change the state, update it, a bit like the reducer, and then finally we have the view code, which takes your model and creates the virtual DOM for displaying to the client. We can see here in the view at the moment we have this image line here and then the text below, and that's what we're seeing in our browser. In order to get a basic Hangman game going, we're going to need a phrase to guess. It's going to be static initially, but we'll change that later, so we can start off by just hard coding it here. I am going to shamelessly choose the phrase like and subscribe. In order to display this in the view as a series of underscores, which might be the way that we like to show something for the Hangman, so we have a series of blanks in order for people to guess, we can create the kind of HTML representing our phrase by taking the phrase itself, splitting it into a series of single characters, and then mapping over that to replace each character with either an underscore if it's an actual letter or leave it as a space. So we're going to take the character that's coming through, we're going to do a kind of inline lambda function here, and we're going to say if char is equal to a space, then we're going to leave it as it is. Otherwise, we're going to make it into a underscore for the moment. That's going to give us a list of strings, and now we need to display this as HTML somehow. So in fact, we're going to map this again, and we're going to have a list of these, well, still kind of characters, but it is not a separate character type because we've done a string.split, so there's still individual strings, they're just one character long. And we're going to put each of these into a span with the text of just the char. So at the moment, at this point in the pipeline, our value is a list of HTML elements. And we're just going to group that together by just throwing them all into a div. So now that list of HTML elements is going to become the children of this div here. And that div is then going to be stored in this final output of our view function. If we go across to our browser now, we can see that there's an error. It doesn't know what span is, which is fair enough, because if we look up here at our imports, we can see we're explicitly importing only certain things from the HTML module. And so I'm going to ask it just to import everything. And that has now changed so that we have this series of underscores at the top that we can see match the pattern of like and subscribe. But obviously for the purposes of the game, we're not meant to know that yet. In order to make this look a little bit nicer, I'm going to copy in some CSS that I've prepared earlier for this demo. It's going to improve the look of this and a few of the other things we add throughout the demo. It's not really worth going into, but it isn't that complicated either. So I'm going to copy what I think is from here into our source folder. And if we watch that recompile, we can now see these letters more clearly separated with a bit of padding between them. Down here, as you can see, we also have this blue box, which serves as the Elm debugger. We can maybe look into that later. For the moment, we can ignore it. It's not that important. Okay, so we have our thing to guess, but we don't have any way of making any guesses. So how might we go about doing this? Well, we want to, for the purposes of this demo, we're going to create a button for each letter you can guess, and the user can make their guess by clicking on the different buttons. So if we come back to our view, we might say that our buttons HTML is going to be the alphabet. I hope I've got that correct. We'll find out. It's probably a more efficient way of doing that. Again, we can split this, if I can type it properly, and we can now create buttons out of all of these. So we've got a list. We're going to take the particular character we're interested in, and we're going to make a button with the text of that character. Again, we need to convert this list of HTML into a single HTML element. So we're going to put them all into a div, and we're going to put the buttons HTML under there. So this should all compile fine, and when we get back, we can see this set of buttons that have been a little bit kind of augmented by the CSS that I've copied in, and that is looking good. It doesn't do anything right now, but at least it's looking like something. So what we really want now is for when we click on a button, we kind of register some kind of guess, and if that guess is correct, then the letter appears in the phrase above, replacing the appropriate underscores. So to look at this, we're going to have to look at starting to modify the state of our application. Our buttons are going to perform some kind of action which updates the state, so we can track the number of guesses or the total guesses we've had so far and show the appropriate letters in the phrase. So if we come back, we are going to change our button so that we use an on-click, and we're going to guess a particular character. So we're going to, when we click on the button, we're going to trigger a guess action with the particular character that we're interested in. If we want to define our guess action, we do it here as a message for our application. It's going to take a string, because remember, our characters are still just single character strings. And the way we handle the update, so we handle these messages as they come into our update function, and generally speaking, we do a case statement on the message in order to to handle the different options, and we can look at what we do with this guess message in particular. For it to completely no op, we would return model and command.none. That basically means return the model as it was and don't do any additional work using the command functionality in Elm. If we compile this, it's going to complain because we haven't imported onClick. So onClick comes from the events, which I'm also going to kind of casually import all of. If we come back to our browser now, we'll see that this will reload. This still does nothing because we're not actually handling the data, the message properly. But what we can see actually down below with that debugger, that number in the bottom corner is ticking up, and we can see that these different guesses are coming in through the system and are displayed by the debugger. The debugger allows us to jump back and forth through the various actions and messages that have happened, and generally see how the model evolves with time. But in this case, our model doesn't have any information in it, so it's not showing that much. If we want to register these guesses, then we want to be changing some kind of state in this line, which means we need a state to change. So we can change our model so that it can store the guesses. We might say we're going to store these guesses as a set of strings. That means that we can't guess the same thing twice because a set only stores unique entries. We need to import the set, so we import the set module and expose the set type. And then we need to, in this init, give it some initial value. So we're going to say that our guesses is an empty set initially. That's going to format and compile, and we can come down to here and say that our model upon this guess is now going to have the guesses field updated. So this syntax is how you update a field on a record in Elm, and we're going to say that it's now going to equal set. I think it's either add or insert. Let's try add and find out how it goes. We're going to do insert this particular character into our set of. So that's not going to work. Let's try it with insert instead. That seems hopeful. So we've now, as we click on this, we should be recording our guesses in the model, and we can have a look over at the debugger to see that that's working. This is reloaded. We can pull the debugger up. I'm going to try and put this on top for the moment. And then as we click these, we can see that our model is collecting together unique characters that have been clicked. If I repeatedly click on X, it's not going to register it multiple times because it's already in there. If I repeatedly click on T, it goes in there once and then stays as it was. So we can see that we're storing these guesses. Now we just need to use these guesses properly. And we can do that by manipulating this phrase HTML down here. So we're saying if it's a space, we're just showing a space, which is very reasonable. We don't expect people to guess spaces in Hangman. But we can also say if the character we're looking at is a member of the guesses we've already got, then we expect to just display that chart, right? So if it's a space, it stays a space. If we have successfully guessed this character in this string, then we show it. If we haven't yet successfully guessed it, we show the underscore. If we come back to the browser now, we can see that it's remembered the states and we've got a couple of them correct. We can show that some of these are available in more places, but if we guess something like W, it's not there, Q, it's not there, J, it's not there. So we've got the basics of a working Hangman example now, which is fun to play around with. Obviously it's not great because if we reload the code, it's going to reload the page, it's going to give us the same thing to test, to guess at, and that's not a very fun Hangman game if we always know what the answer is going to be, but the basic principles are there. And something we might do to make this a little bit more friendly to the people playing is to show them what they've failed to guess. Okay, so we want to look at this guesses array, see which ones aren't valid, and show them as a list underneath. So we've got all the data we need really so far to do this. We could say that our failures HTML, don't worry about this HTML suffix all the time, like I don't love it, but I kind of do it to stop clashing with other variable names sometimes. Elm doesn't allow you to shadow variable names, so quite often you'll end up adding little suffixes to distinguish different things if you've tended to use the same variable name throughout your code. So for our failures, we want to look at the guesses we have, so we can look at guesses in our model. We can convert that to a list. So a set to list is going to give us a list of these strings. We can then go through and say, well, if we take our actual phrase and make a set out of that, so we could say our phrase set is going to equal phrase string.split and set.fromList. So this is phrase set is now going to be a set of characters which contain all of the letters in our initial phrase. And we can now filter out this list. So we can say list.filter, and we've got a character that we've guessed, and we can say we want to keep it if it isn't in the phrase because we're showing it as a failure. So it's a failed guess if it's not in the phrase. So we're going to show it in this list of failures if it's not there. So we're going to use the not function. So Elm doesn't use a singular kind of unary not operator. It uses the not function instead, and this is sort of partly in its sort of history as ML languages. Generally, operators should always have two arguments, one either side, and so it doesn't have a unary not, it just has the function instead. This also allows you to kind of more easily use a not function in pipelines and other circumstances, which is useful, but it can be a bit confusing for beginners. And we want to say if it's not a member, this char is not a member of our phrase set, then we want to keep it around. And we're going to, I guess, also list.map change this into some kind of span. So we can clump it all together in a div as well, and we can say failures HTML under there. Try and compile that. That looks successful. We come back here, we can see all of the failed guesses under here. So if I reload this to wipe the slate clean, if I guess G, it's not in the phrase, it appears under here. W, not in the phrase, it appears under here. If I click A though, it is there. And so we have our nice distinction between successful guesses and unsuccessful guesses. The next step we might look at is providing a slightly nicer way of restarting. So, you can reload the page, but maybe to make this a more self-contained experience, we would like to be able to restart our Hangman sessions just by clicking on a button. So let's have a look at doing that. We want some kind of button down here with the text, which is just going to say restart. And we're going to say on click, we want to restart our whole game. So that's going to be a new message we want to handle. We can put restart here. If this comes through into our update function, we want to do something with it. And what would restarting look like? Restarting would probably look like emptying the guesses. Okay, so again, our game isn't brilliant because we're going to have the same phrase every single time at the moment, but at least we can empty the guesses to start again. So that compiles successfully. We can see here we have this restart button. If I start guessing at random things, we can fill up some detail, and if I hit restart, it disappears again. So that gives us a nice restart mechanic, which is useful. So the next thing we might want to look at is the fact that our guessing phrase is the same every single time. Like, it's not that much fun for people to play this if it's the same every single time, so we want some way of sourcing new phrases. In order to do this, we're going to look a little bit at HTTP requests in Elm, just to cover that too. We could just build like a list of phrases into our Elm source code and randomly select one each time, but instead we're going to ask for one from a little server API that I've already set up. In order to make this happen, we want to move our phrase into the game state, so let's do that initially now. So instead of it being stood out like here, we're going to say our model also includes this phrase, which we will start with that definition, but evolve as we request more values from the server. So this changes our model definition, this changes the initial state of it, and that should, well, instead of using this phrase, because that's not globally available anymore, it's part of our model, we want to change those references as well. That's compiling, and hopefully this will reload and will work as we expect. So that's still working. Our phrase is now a dynamic part of our state, and we want to look at how we can load a new version of a new phrase each time that we play this. So maybe when the game's loading and every time we hit restart, we want to get a new phrase. In order to request a phrase from a server, we need a server to request it from. So I actually set up a little project on a service called Glitch. I'll load it up here. This allows you to run, to make little Node.js projects, including being able to run, run these projects, run little servers, respond with things. So here I have a JS file. We're not going to go massively into the detail here, but it uses the Express package to serve up words on this /word endpoint. The words it serves up, it also serves up stuff on a /level endpoint as well, but it's going to serve up a random word sampled from this list. So you can imagine this is a big server that has loads of different options when you get a genuinely kind of random word to guess each time, but for the moment we're just going to confine ourselves to this list. And these are the sort of headers required to allow us to request the data from the Elm side. So we're going to have a look at how we're going to do that from Elm, and in order to do that we need the HTTP package. So Elm, doing HTTP requests isn't built into the absolute core of Elm. Instead it's in this kind of main package provided under the Elm namespace, which means it's kind of one of the central packages. And we can see here a basic example of how to do an HTTP GET in Elm. So the first thing we need to do is install this package. If we go back to our terminal, we can do elm install elm/HTTP and say yes to all of that. I'm also going to install JSON because I know that we're going to be decoding the response that will be in JSON. And so, yeah, we might be anyway. Let's have a look at that. And so we can now return to our code and try and set up something like this. And we can notice from the example here that this HTTP request is going to produce a command. And we've seen these commands a little bit already, although we've largely ignored them. Commands come into play in the update function. So here we can see this is going to return a model and, a model and a command as a tuple. And it's this command that we're going to use. Commands in Elm are used to execute side effects, so things like reaching out to an external server and requesting some information is considered a side effect, and therefore it is managed through this command system, which is only accessible in the update function. You can't, run a command from inside your view code or something like that. So we want to look at some different options. One thing we could start off with is when we hit restart, we're going to fetch a new word. All right, and if we encode our fetch word is going to be something that is going to run one of these commands, if I could type. And in order to do that, we're going to use this HTTP GET request from before. So we've got a URL and then some kind of expectation. We're actually more interested in following this expect JSON example down here, but let's get it going. So we're going to get, and we're going to get a URL, and the URL we want is this. So this is the hosted version of that project we were looking at before. So we're going to do a get here, and is it expect? So expect something, and I'm just going to double check how this is working. So our project is going to return a JSON value, which is going to be a JSON object where the key is word and the value of that key is the word we actually want. So we're going to have to decode this little chunk of JSON. So we are going to expect some kind of JSON value. We're going to give it a message to handle this new phrase with, so we can call this new phrase. And then we need to give it some kind of word decoder here. So the new phrase is going to be a message we can put up here. It's actually going to have to deal with the fact that this HTTP request might fail entirely, but if it succeeds it should just have a string, which is our new phrase. We're going to jump around a bit. I guess for the moment let's add this as well. So this is going to come in with some kind of result. We can sort of lazily just say, what is this result? If it is a new phrase, we can come in and say, that's great, I want to set the phrase on my model to be this new phrase, and we don't have any commands to provide. And in the error case, I'm just going to ignore it, which is pretty shocking, but we can come back to that later. So that should have successfully dealt with the result of this, with this message coming back through from our HTTP request. But we still need to look at this word decoder. So decoding stuff in JSON, decoding stuff in Elm is like a whole thing in itself. It's quite different to maybe working in pure JavaScript or TypeScript, where you can frequently just request something from the server and then just sort of, you know in your own code the shape it's going to have and you just work with it. Because Elm is statically typed and compiled, it adopts a strategy where you have to decode the incoming JSON so that you state like, this is the shape I expect it to be in. If it is in this shape, give me the result I'm looking for. If it's not in this shape, then give me some kind of error and let me deal with that. This means that generally speaking, you don't ever have any runtime like exceptions in Elm, because this data coming in from the outside world either matches expectations or it doesn't, and you get a nice error result, or like a result value which encapsulates that success or failure without kind of throwing some kind of exception through your code base. So we're going to define this word decoder, and this is going to be a decoder for a string. And it takes a little while to get used to how these things work, but basically we're looking for that word field in the object that's coming in, and we want to decode the value of that word field as a string. Now we're going to have to improve add a couple of imports here. So we need to import our HTTP module. We also want to import our JSON decode module as decode. That's how I generally do it. And if we compile this, it's going to say it can't find the decoder type, because we can also expose the decoder type from here. Okay, that is successfully running. That should work every time we hit restart. Let's see how that goes. We switch back to our browser, find our LMAP. When we hit restart, we can see that, oh, it is changing. That is nice. So if we look, every time we're hitting restart, it took a moment to, I think, for the server to spin up on its side, but now it's being quite responsive, and we can see the number of underscores changing. And if we start trying to guess some very bad guesses, we can see that we're getting kind of delightful language come through here. Some other guesses also similarly unsuccessful. Wow, I'm very bad at this. We're going to have a no runtime exceptions by the looks of it coming through here. So that's working really well. Now, one thing we want to clean up a little bit is, of course, every time we restart the app, we go back to this like and subscribe thing that's been hard coded into the init function. So we want to look at using that init function to get a random word off the start as well. So if we come back, we can look at init, and we can see that actually on top, as well as the update function, init also returns a model and command. So we can set our phrase to maybe nothing initially, and we'll come back and improve this, but then we can run fetch word from here as well. That should compile. This is reloaded, and now every time I reload, it's going to go off and fetch a new word, and we're going to get a different word each time. So now we're much closer to a reasonably useful, handy game, and we can see whenever we hit restart, we actually have a single message in our debugger already, because it's already called this new phrase and has come back with the word that we want to decode. But there is something we can improve about this. So if we look at our code, we can see this initial slightly less than ideal step. Our phrase is set to an empty string whilst we wait for the word to be fetched. There should be a better representation of this. This phrase isn't really an empty string initially. We'd rather store some more useful state about what's going on. So we can try and take this a little bit further, and we can start introducing these custom types that Elm has to model data so well. And we can really say that our model isn't going to be just one of these two things, or just this sort of record of these two values. Rather, this is actually our kind of working game state when everything's kind of going well, and in fact that our model is best represented as something that is either loading, is running with some kind of game state, or is perhaps in an error situation if the HTTP request has failed. So this is one of the nice things about Elm. I can just come along here and say, well, really, this is how I now want to be representing my model. And when I hit compile, it's going to show me all the places where, you know, that is no longer true. So I might say, we can come down here and have a look at this init function. Obviously, the model is no longer, like, this isn't a valid value for it. So instead, I might say, when our program is initialized, the model is just going to be in a loading state. It's going to be in a loading state because we're, you know, immediately fetching this word the second it starts running. So it's immediately in this loading state. If we come through here, we can now see that our model is in a, like, this is no longer a valid update to our model because our model is either in this loading, running, or error state. So if we are in this guess mode, and there are different ways of handling this because we're obviously going to have to do like a case statement to look at our model and see what state it's in and to know how we can update it. And it gets a bit clumsy having a case statement inside a case statement, so there may be different ways we can look at doing this. But for the moment, we can say for our guess, we can say in the case that our model is in our running state with this game state, we can say that we want our model to still be in the running state with the game state, and that the game state's guesses should be updated to include the new value plus the old game state guesses. So this thing I'm highlighting now is our entire model, and so we're still returning a model and a command from this function. It's just that if it's in any other situation, we kind of don't really want to do anything with it. Like, there are better ways we can handle this, but we're basically saying if it's not in a running game state, I'm not interested in registering a new guess. It doesn't do me any good. If we are restarting, because we're now fetching the word again, we can just return this to a loading state because we are loading the new word technically. And then we can say when this new phrase comes in, if we have successfully got this phrase here, we know that our model is going to be something running with this game state. So the phrase is going to be the phrase that's come in, and our guesses at this point is just going to be an empty set. So whenever this new phrase thing comes in, which either means we've just loaded the page or we've recently hit restart, then we are going to, on a, you know, in a successful state, reset our game state to be running with the new phrase and no guesses. If the HTTP request is an error, though, we can actually change our model to reflect that and say that this has been an error. We still have probably a couple of different places left to change, but this is one of the nice things about Elm, that you can just run the compiler again and it's going to take you to the next place where something invalid is happening. So again, this sort of state of the model no longer exists. We have to look at the model, see whether it's loading, running, or errored before we can start doing something like extracting the phrase and the guesses. So what we're going to do here is add a kind of new layer to our view, which is to say we're interested in what's happening when it's loading, when we're just going to throw in some ugly looking loading text. If it's running, we've got the game state, which is great, and we can do a kind of view game state with that game state. And if it's errored, then we're going to have something like the loading, but with error here. And now obviously we want that view game state, but view game state is going to be, you know, the same implementation as we had before. So I can leave it like this. If I compile it, oh, it's not very happy. I can change this to be game state all the way through. Oh, and back. If I compile that, sorry, it's taken me too far. So you'll see that this is now compiling, it's happy again. And what's interesting is I haven't provided a type signature for this function. So in Elm, you actually don't need to provide type signatures for anything. The compiler will analyze all of your code and infer the type signatures from what you're doing with the various bits of data in your code. But it can be much nicer to provide type signatures, because then you're saying, well, I believe at this particular point in my code, this is what I'm doing. And it means if your compiler disagrees with what you're doing, it can give you a much more isolated error message. It can be like, well, actually, in this particular function, I don't think you're doing what you think you're doing, as opposed to, it's saying in your entire program. And you can have this. Sometimes I write quite a lot of code without type signatures, and you can have a situation where it's saying, like, right down here, I don't think this is what you think it is. And you've got like 500 lines of code to analyze, because you realize there's some kind of weird inference where it's realized that you're using some part of some structure in a certain way, and it no longer lines up. And it's actually much better to just provide a lot of type signatures so that you don't get into that confused state. So we have this game state, and it's going to match the same output as the function above. If we now jump across, we can see that initially it's loading. It goes very quickly because the server is quite responsive, but initially it's loading. We can then make our guesses. If we hit restart, it goes back to loading very quickly before it shows the new string. And we can demonstrate the error case here, I imagine, by changing a few things. We could change the URL so it hits a wrong URL. We could also change the decoder here so it's doing something that's not valid for the data that's being returned. So if I look to return this, we're going to see that it's an error. It immediately goes to an error, and there's nothing we can do about it. If I restore this though, when this reloads, it's going to come back and work properly. So that actually brings us to the end of this demonstration. We come back here, pick up a few highlight points. This is called a custom type in Elm. Sometimes it's referred to as an abstract data type or algebraic data types. In other languages, Elm sort of seeks to choose simpler language where it can, so it uses the phrase custom types. It's an incredibly powerful mechanism. These types can be kind of arbitrarily complex. If I wanted some record of the loading state, whether there was like a previous error or something, I could add additional values in here. You can just sort of nest additional data structures, have more and more complicated things, and it's a really nice way of thinking about the problem. Like quite often, if you were doing this in some languages, you would instead change this to be a kind of a record that had some kind of like loading, like am I loading Boolean state to it, and then you'd have a game state on top of that, and you'd have a kind of is errored Boolean as well, or something like that. It would sort of look like this instead. I've clearly done something wrong to make it unhappy. And the problem with this is that you can represent impossible states. So you can say, like, I am loading, I'm also errored, I also have some valid game state, all at the same time. Or you could, have none of them in a valid state. And it leaves it in it's much more confusing about how you're representing your data. When you use something more like this, then it's very clear, like this whole model can either be loading, it can be running, or it can be in an errored state. And depending on which thing it is, I only have access to particular information. I do not have access to the game state if I'm loading. Therefore, I couldn't possibly draw the kind of the buttons and the board if I wanted to. The same in the error, like I have to recognize what states I have, and it's best if I design my data in a way that it only handles those states. Otherwise, we can see other patches like use of commands to interact with the outside world, use of decoders that we haven't gone into in a lot of detail here. Maybe I'll do that in a different video. Simple case statements to inspect data and only act on the states that we want, ways of ignoring data if we want. And then again, those case statements come into play really nicely when we're drawing our virtual DOM. We can only possibly draw the game state if we have a valid running game state. Otherwise, we're very limited in what we can do. And just the joys of using pipelines in Elm, which are quite common in other languages as well. I think possibly initially inspired by F#, but popular in Elixir as well, and coming into possibly even JavaScript at some point, which is a fascinating thought. And yeah, that's it. I hope you've enjoyed this introduction to Elm. I really like working with the language. There are some kind of pros and cons when you get like really deep into it, but essentially this developer experience of having a fast compiler with helpful error messages and a kind of data first sort of approach to programming is incredibly useful and an absolute delight. And I've since used some other programming languages after using Elm for a very long time, and you really do start to feel some of these differences. And you miss it a little bit. So I recommend giving it a go if you haven't. I hope this has been a reasonable introduction, and thank you.
Thank you for watching the video. I hope you enjoyed it. Please like and subscribe if you'd like to see more. And if you have any questions or if there are any topics you'd like me to tackle in future videos about Elm or anything else, please leave a comment below.